Welcome back. We were just talking about what will happen to the sun after it runs out of hydrogen in its core. And so I drew a picture in the last video that sort of tries to explain why it is that the core contracts and therefore why it must heat up, and why it is that hydrogen is still burned in a shell around the helium core. We've seen that that causes the luminosity of this star to increase dramatically, as well as the exterior radius. The outer regions of the star go out dramatically. The last thing on this slide to think about is the temperature decreasing. Let's try to think about why that is. It's not obvious. If you remember our luminosity formula, here's our star again. Remember our luminosity formula, it is luminosity equals, there's some constants, so as this star gets more luminous and larger, it's not obvious what happens to the temperature, because both of these are going up. The temperature could either go up or down. It turns out that this square, though, makes a big difference. And so both the luminosity and the radius increase a lot. The temperature actually, the surface temperature goes down because the radius increasing, the square power of the radius increasing beats the luminosity increasing. And so the surface temperature of the star will generally go down as it gets larger and more luminous in this particular case. So we have the luminosity and the radius increasing, we have the temperature decreasing. What will we see from the Earth? Obviously, if we're watching the sun do this from the Earth, this is a low mass star now we're talking about. We're studying with the low mass stars. What will we see from the Earth? The sun becomes a giant star. And this is not a small effect. This is not a subtle change in luminosity. This is not a subtle change in radius. The radius of the sun increases enormously. The radius becomes a half an astronomical unit. It reaches, the physical surface of the sun reaches halfway between the center point of the sun and the Earth. Mercury is physically inside the sun at this point. It is gone. Venus, although it technically is still outside the sun, it's so hot there now that Venus becomes vaporized as well. These planets are just gone. The Earth isn't doing well either, but at least it's still around. The luminosity, again, this is not a subtle effect. It increases by a factor of 2,000 in this particular region, particular phase of its evolution. And as we mentioned, the surface temperature, the temperature of the surface, the core temperature is going up, but the surface temperature is actually going down as we go up, as the star evolves. Okay, so here is a picture of what this might look like. Here is the diameter of a main sequence star like the sun. It has a diameter at this point of roughly 1/100th of an astronomical unit. As a red giant star, it's going to be about 100 times larger than that. The diameter is going to be a full astronomical unit. Oops. The radius will be about a half an astronomical unit. So the Earth on this diagram would be somewhere out here. Mercury is like here. Venus is like here. It's filling a large portion of the inner part of the solar system at this point. We know that this happens. We see stars that are physically this large. This is a picture, an old picture of the star Betelgeuse, which is this star in the head of Orion, or the shoulder of Orion. Interestingly, this star, we've talked about it previously in this class, is doing some very interesting things this semester. But this is one of the this is an example of a supergiant. It is an extraordinarily large star. It's large enough that with the big enough telescopes, we can actually image it. We can actually get, most stars are just points of light, but Betelgeuse is big enough that if you have the right equipment, you can actually see different parts of the surface of Betelgeuse. Again, this is a much more massive star than the sun is, but here is the size of Earth's orbit. Here's the size of Jupiter's orbit. Betelgeuse itself is way bigger than the Earth's orbit or Jupiter's orbit. It would dominate the entire solar system. all of us would be vaporized at our distances if we were that far away from Betelgeuse. So this does happen. Betelgeuse is a much more massive and therefore much larger star at this point in its stellar evolution, but we can see that this actually does happen. Okay, so here's a question for you. Where will the star move on the HR diagram at this point? It has gotten more luminous, it has gotten larger, and it has gotten cooler. Where is it going to move on the HR diagram? I'll pause. Well, you can pause the video and answer, and then come back and we'll talk about where it actually goes. Okay, I'm back. So it has gotten brighter. Brighter, more luminous means up on the HR diagram, and it has gotten cooler. Cooler means to the right on the HR diagram. So it must have moved up and to the right on the HR diagram. This also means both of those imply larger physical sizes. And so it's not surprising that we call these things giants. They are enormous compared even to their enormous main sequence counterparts. So what does this actually look like? Here is an HR diagram. This is what we think something like the sun will do, whoops, as it leaves them after it leaves the main sequence. It will do a little funny dance down here. We call these different things. This is the red giant branch. We have a little subgiant branch here. But the main point is the entire sun will go through a series of processes that will make it much cooler and much brighter, much more luminous. And it becomes a red giant. And it moves off the main sequence and moves up and to the right. It gets brighter and cooler. We call it a red giant. Okay, well, this is going to continue going. The sun will continue to run out of hydrogen in its core. The region in the sun's core where there is no hydrogen anymore will get more and more massive. There will be more and more, a larger and larger region at the center of the sun where there is no longer energy being generated. And so this process will just, this is a fairly slow process, but it's a continual process. As more and more of the central part of the star runs out of hydrogen, it gets larger and larger, it gets more and more compressed, it gets hotter and denser. The luminosity, the energy being generated goes up, and that pushes the outer part of the star out more, and this star will continue to rise slowly up the red giant branch. This is a process that in the sun's case will probably take millions of years. But that's a far cry from the billions of years that it spent on the main sequence as it goes up to the top of the red giant branch. Okay, so eventually things start to happen in a weird way. So let me erase my previous thing and bring back my whiteboard. Okay, hopefully you can see that. And let's draw our star again. So here is, again, the region of the star where hydrogen is burning. The outer part of the star is sort of out here, although this is not to scale anymore. It would be way outside of the building on a real scale, but you get the idea. So at the center of this, there is an ever-growing region of helium ash that isn't burning anything at all in the center of the star. And all of this material continues to bear down and beat down on it and get hotter and denser. And it just continues. It gets hotter and denser and hotter and denser and hotter and denser. Now, there comes a point where this is no longer possible to get hotter and denser. So let's go back to my slideshow. What happens eventually? The core continues to contract and heat. As the helium core gets more and more massive, the density eventually reaches a fundamental limit. There's a principle in physics called the Pauli exclusion principle. And the Pauli exclusion principle says that particles of a certain type, namely fermions, cannot get any closer than a certain amount. Basically, if you have a box and you try to put a whole bunch of these fermions in that box and squeeze them close together, they will exert a pressure on themselves that keeps them from going to a higher and higher density state. the difference, the Pauli exclusion principle specifically says no two fermions can occupy the same quantum state or same quantum energy. It's a mouthful, but what it basically means is this: by fermions we mean neutrons, and we mean electrons, and it's actually electrons that become important here. The electrons, as we try to squeeze these things together, say, hey, wait a minute, I can't get these two electrons closer together than they already are, because if they did, they would be occupying the same quantum state and the same quantum energy. Now, two electrons can be in the same place at the same time if they have different energies. And so what happens is you try to squeeze more and more of these electrons into a smaller and smaller space, is that some of those electrons are forced into higher energy levels. They have to be moving faster physically. And so that becomes difficult to do, though. And so there comes a point at which the core of the star cannot physically get any smaller, or the electrons would be moving just way too fast. And so that leads to a fundamental stop. So the helium atoms become so closely packed together, they have virtually the same energy, density, pressure, and temperature. Now, what does that look like? I'm actually going to pause the video here, and we'll start the next one, and we'll see what happens in the center of the sun when this Pauli exclusion principle sets in, and how that affects what happens next. Okay, stay tuned.